Okay, so today we're going to go through the Chapter 11 quiz review. We're going to find the mean, median, mode, range, standard deviation of some data, work with the data, and statistics that we've worked with up to this point. So the first thing we need to do is we need to find the mean, median, mode, where I'm going to write the range, and of course our standard deviation. Now, for these values, I'm actually just going to rely heavily on my calculator. I'm going to start by going in, finding stat. I'm going to edit the data. I'm going to clear out the data that I have here. So go up, clear, enter. And then I'm going to enter the data. See, 8, 3, 18, 9, 5, 6, 4, 4, 7, 4, 3, and 2. Now it's really important that you put this data in correctly, that you don't miss anything, because there's not a lot of partial credit you can be given if all your numbers are off because you mistyped something. And if I don't know what you mistyped, I don't know if you're just guessing or if you legitimately made a small mistake. So I'm going to take a real quick check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 entries. And if you look over here at the calculator, it says my next entry would be my 13th. So I have 12 numbers. So here's hoping that we've got them right. I'm going to go to Stat, over to Calc, and I'm doing one variable statistic. So I just press Enter down to calculate. So right here I have a mean of 6.08. That's my top number. The other thing that shows up on this front page is our standard deviation, which is right here, 4.13. So we'll come in right 4.13 there. The range and other things might be found a little bit further down here. So, for instance, the range is the max minus the min. Well, the max is 18, the min is 2, so the range would be a range of 16. The median is stated as 4.5, that's right in the middle there. And then the mode is the most common number. Now this one I'll just take care of myself. As I look across this list, I see the number 4 shows up 3 times. 3 shows up twice, but that's it in terms of duplicate numbers. So the most common number was 4. Okay, now the problem with this data is it actually has an outlier. It has a piece of information that doesn't fit with the data. If you look specifically at the 18, that's a problem. Now in question 1, you're supposed to do the data with that error in there, with that outlier. Maybe it's not an outlier, maybe it belongs. But now we're going to remove it. So it's important you know how to identify if something's an outlier. So it should look far enough off that you would notice that it's just so different from the rest that we're going to try to do the same test of information without that outlier. And we're going to see what happens to the different data. An outlier, if it's a valid data point, might be really important to keep in the data. But in a case where we think, man, that data I don't think that 18 belongs, I'm going to come to the 18 and I'm going to delete that individual entry. Now I've only got 11 entries, so some things will change here. Sorry about that. So now we need to find the same data. So we're going to come back to our calculator, Stat, slide over to Calc, run the one variable statistic again. This time my mean is down to 5, which is a little bit more toward the center of my data, which I like. My standard deviation has been cut quite a bit. It's now 2.13. Okay, the rest of the data I still need to go down to find that. My median is now 4. My range is 9 minus 2, which is 7, a much smaller range. My mode didn't change. I didn't get rid of a 4 or anything like that, so I should still have a mode of 4. So the first two questions are really easy. They're very calculator dependent. And now when we get to question number 3, we're going to come down to our understanding of a normal distribution and how to use it appropriately. So I want to know the probability in a normally distributed data of lying between x bar minus 2 sigma and x bar plus 3 sigma. So the first thing I'm going to do, I'm going to come and I'm going to try to find x bar minus 2 sigma, which is right here, right there. So I'm going to come in and I'm going to draw a little cut line. And then I need x bar plus 3 sigma, which would be right here. Okay. If you notice, x is living between those two cut values. So I want the probability of being in this region in between the two? Well, they're all labeled, so I've got 13.5 plus 34 plus 34 plus 13.5 plus this last one is 2.35. I can do it that way, or I can say I have 100%. Let's subtract out the corners, the edges. But I'll just take my calculator real quick. I've got 13.5. I've got two of those. So I'm going to times that by 2. Plus 34 times 2 plus 2.35. And you can add those up however you want. Add them up one at a time or however. We should get a probability of 97.35%. Okay? That's it. Just reading the table a little bit. Now, with this next question, we're going to be given data and information that doesn't fit the normal distribution table perfectly. So I'm going to draw my own normal distribution just to kind of get a baseline. Okay, it doesn't have to be perfect. Right down the middle is my mean, and it says that the mean is 14. Now the standard deviation is 2.8, which means to get to the next cut line on the front page, I'd have to go over 2.8 to 16.8 or down 2.8 to 11.2. I'd have to go one way or the other, and I'd have to go by that size. The problem is the number we're being asked about is the number 16, which is not exactly one standard deviation or 2 or 3. It's less than 1 standard deviation. And we're being asked what's the probability that a data point will be less than 16. Now less than means to the left. Okay. So I want to know what's the probability of being over here. Well, to do this correctly, I'm going to have to use the z-score, which is just this formula right here. I'm going to have to use it for 16. Now the first number in the formula is the number of point of interest minus the mean, which is 14, and divide that by the standard deviation of 2.8. Now I'm going to want to know exactly what this is. When you do it in the calculator, 16 minus 14 has to be finished before you divide by 2.8. If I type divide by 2.8 right now, I will get a wrong answer. So I'm going to do that. Obviously it was 2. I could have just done that by hand or in my head. I divide that by 2.8. I get a z-score of 0.714. Now, the truth is, on a z-score table that we have, we can't be this accurate. So we can only have one number in front of the decimal and one number behind the decimal. So this is the same as 0.7. This does not mean 70%. Okay? That means that that is the number I need to find on this table. So I'm going to come to 0. Now notice, there's a positive 0 and a negative 0. Because I'm on the right, clearly my 0.7 is positive. I'm going to use this positive 0. And I'm going to scroll over, slide over till I get to 7.7. So 0.7 lines up right here. Okay, so that tells me that 75.8% of data will lie to the left of my 16. Now this is important. If I'm looking for the left side, that's my answer. If I'm looking for the right side, I would have to subtract that from 100% to see what does exist over there. Because I wanted the left side, I can circle that and be done. Be aware, you need to look at that picture, draw it, kind of have an idea of how do you read it. But the standard normal table is always to the left. So if it's not to the left, the standard normal table will help, but you still have to do some more reasoning before you're done. These last two questions come from the end of 11.5 and 2.6, the last stuff that we did in our work. And what we're going to do is we're going to throw this into the calculator in our data, and we're going to go from there. So let me clear out what I've got in my calculator. I don't want anything in there. Alright, so we're going to go Stat, we're going to edit, we're going to put this data in. Let me again clear everything. -3, -2, -1, 0, 1, 2, and 3. Then over here in L2 I've got -12.9, -9.4, -5.9, negative 2.4, 1.1, 4.6, and 8.1. So there's my data. The problem is I need to know, is this linear, quadratic, or exponential? To figure that out, I'm going to need to look at it on a graph. So I want to turn on my stat plot. So I'm going to second y equals, that's where my stat plot is. I'm going to go ahead and I'm going to turn it on. Now, the other issue is that if these data points don't show up in my XY axis, in my graph window, I'm not going to be able to see them. So I'm going to go ahead and change my window. The lowest x I have is negative 3. So I'm going to use negative 5. I don't want to be running into the numbers. I'll go up to 5, and counting from negative 5 to 5 by 1 makes sense. The lowest y value I see is in negative 12.9, so I'll do negative 15. The biggest one is 8.1, so 10 makes sense to me. Maybe you want to count by 2s, maybe you want to count by 1s. That's up to you. Now if I go and look at the graph, I can see the data plotted, and I can see all of the data, all 7 points that I tried to plot. This clearly looks like a line. So I know I want to use a linear test, or linear regression. One other thing that you should consider doing, and the calculators will get reset, so you have to do this by hand, but if you really want that confidence and you want to tell somebody, hey, I know this is right, you would go down and you would turn on your stat diagnostics. Okay, notice mine's already on. And that's an awesome deal. So I want that kind of to my favor. Again, it just tells me about the R value, or the R squared value, and gives me a real sense of how accurately it all fits. And we said it was linear, so I'm going to go ahead and run number 4, the linreg. And here I have the equation y equals 3.5, that's my A, and that goes with x, plus my b, which is a negative 2.4. Or more appropriately, y equals 3.5x minus 2.4. Notice the r value is exactly 1, which also means the r squared value is 1. When the r is 1, that means we have a 100% fit. Sometimes you'll notice that the r value is negative. If the r value is negative, it doesn't mean it doesn't fit. It just means that it's a downward trending line. Again, if we went back to our graph here, this is coming upward, so it would be a positive r value. If it was going downward, it would be a negative r value. What we are worried about is how close is it to 1, or in the negative case, how close is it to negative 1. All right, so let's do another one. We're going to do this other problem, number 6. I'm going to go ahead and edit my data. Fortunately, my x's stay the same. If it's a little hard to see, I'm just going to go ahead and read those off and type them in. I have negative 243.2. Okay, now something's going to happen here. Let's keep going. Negative 60.8, negative 15.2, negative 3.8, negative 0.95, okay, negative 0.2375, and last but not least, negative 0.0594. Okay. Now when I go to do the viewing window here, I really want to look at these numbers again. My lowest x is negative 3, biggest is 5. That makes sense to me still, because I'm still using those negatives. But my y min is way, way lower than that, so I need to go to negative 250. Let's do that. And it looks like I never quite get to the positives. They always stay negative. So let's just go up to, say, 10. I don't really need to go that high necessarily, but give myself some room. And I'm going to count by, let's say, 10. We'll go about there, counting by tens. Now if I go and I look at the graph, this clearly has an exponential curve to it. It's dying off, but it doesn't come back up. If it'll come back around. If it had more of a U shape, I would go quadratic, but this looks exponential. Now this is an interesting thing that Mr. Henry and I actually ran into and had to discuss. The calculator's way of doing regressions is a pretty complicated process. When things are negative, in the case of exponential regressions, it is extremely difficult for the calculator to manage. And so the calculator just gives up. It says, this is too much. You need to help me out part of the way. So if, okay, you're doing an exponential, this only happens with exponentials, and your numbers are all in the negatives, okay, what we're going to do is we're going to change something in our stat regression. Before we can regress, we're going to have to change all of the y values to positives. Now I know I'm going to be off by that sign, so I know that my equation is going to have to be y equals negative something. I'm going to take the negative out of the numbers right now, and by doing that, hopefully be able to make it easier for the calculator. So 243.2 without the negative, 60.8 without the negative, 15.2 without the negative. Now this is only happening because all of them are negative, and the calculator is going to have a hard time dealing with that. If it wasn't all negative, we'd be fine. And the x values don't matter. It's only these y values. And it's only because it's exponential in nature. If it was quadratic, it would run the regression just fine. So now I'm going to come over to regressions, and I'm going to find my exponential. Remember, there's only 3 that we're doing in this unit, and it's exponential, linear, and quadratic. Okay, so now I get y equals negative. It doesn't have the negative, but I'm assuming I have to write it 3.800. I'm going to leave that times 0.25 to the x. And what's my r value? My r value is a negative 0.99. Okay. So this is a case where maybe you want to compare r squared values, because these look like they're very different. The r squared here was 1. The r squared here is a positive 0.999. Okay. And so what that does for me is it allows me to compare the goodness of fit between different values. For instance, what if I actually ran a quadratic regression? Here I get an r squared value of 0.885. Clearly this is not as good of a fit. It's a good enough fit if it's the right problem and it's just the best fit I can find. But when I can compare that to a 0.99, I know that I prefer the 0.99. So there's my answer. Okay. R squared values aren't required as part of the problem, but they do give r or r squared values, but they do give us a sense of how accurate is this. It makes your equation and your data way more believable, and so they're just good things to have around. All right, good luck, and we'll see you in class.